9.8 Lesson 1 Power Series. Objectives, you will know the definition of a power series. And Objective 2, you'll be able to find the radius of convergence of a power series. You will determine the endpoint convergence of a power series to find its interval of convergence. So vocabulary for today, power series centered at C. What do we mean by the radius of convergence, endpoint convergence, and interval of convergence? We've actually worked with power series. We looked at an example when we did section 9.6 lesson 3. Today we'll look at the definition of a power series, and we did define it when we were doing 9.6 lesson 3. Today we're just going to look at the definition as it is presented in the textbook. So a power series can be centered at 0, or it could be centered at some other number. So in the second case, it is centered at a number other than 0. In the first case, it is centered at 0. And just to connect this to what we'd been doing in 9.7, in 9.7 we had Taylor polynomials that were centered at C, and Taylor polynomials that were centered at 0, which were called Maclaurin polynomials. And we'll be looking at more of these concepts as we continue to close out chapter 9. So here we have a power series centered at 0. Here we have a power series centered at C. So what is x in a power series? It is a variable, and it could represent some number. So the index is a different variable. It's n. So we have a sub n, which is some constant value, and x is a variable, but once you choose x to be a particular value, such as you choose x to be 20, then it becomes fixed at 20. But in the series, n will vary from 0 to infinity. So that's a power series. The only difference between the first and the second is the center of the power series. More generally, an infinite series of this form is a power series centered at C, where C is a constant. For example, you could have a power series that's centered at 2 or -5, etc. And again, just like with the first example, x is a variable, but once you choose a particular value for x, it becomes fixed. You could choose it to be something outrageously large, like 20 trillion, but once you choose x to be 20 trillion, it would be fixed at 20 trillion. So x could be any number, but once you choose it, it is fixed. In the series, it is n that goes from 0 to infinity. So to simplify the notation for power series, just so we can write what we've written here, to simplify the notation for power series, we agree that x minus c to the 0 is equal to 1, even if x is equal to c. All that means is, if you look at the first term here, it's a naught. Basically a sub n when n is equal to 0. And all this note tells you is that so that you can include this particular first term of the series as described by this notation, when the notation says from n is equal to 0 to infinity, a sub n, x minus c to the n, if you substitute 0 for n here, what do you get? You get a naught times x minus c to the 0. So what happens if x is equal to c? When x is equal to c, c minus c would be 0, and you'll have 0 to the 0. So we're just saying, for the sake of simplification, when it comes to notation, we will agree that x minus c is equal to 1, even if x is equal to c. That's all that says. Normally, this would be undefined. So here we have theorem 9.20, convergence of a power series. And again, you've done problems with power series, so you've already seen this in the work that you've done. But now we state it formally. For a power series centered at C, precisely one of the following is true. And you've seen all of this. Either the series converges only at the single point C, or there exists a real number r greater than 0 such that the series converges absolutely when the absolute value of x minus c is less than r and diverges for the absolute value of x minus c is greater than r, or the power series converges absolutely for all x. So those are the only three possibilities for convergence of a power series. Now, we do have to say something about number 2 here. If this is the case, you also have to consider what happens at the endpoints of the interval and check for the convergence of the power series at the endpoints to determine what we call the interval of convergence. So this number r here is called the radius of convergence of the power series. It basically tells you how far from the center the power series will converge. If the series converges only at the center, the radius of convergence is 0. And if the series converges for all x, the radius of convergence is infinity. The set of all values of x for which the power series converges is called the interval of convergence of the power series. And as I said, in this particular case, you also have to check for convergence of the power series at the endpoints of the interval. We will begin by looking at an example for case 1. I will refer you to an example that we've already done when we did lesson 9.6, lesson 3 a few days ago. So I will refer you to this lesson that we've already recorded a few days ago, 9.6 lesson 3, for something that demonstrates case 2 here. And then we will do an example for case 3. So here we look at number 91. Find the values of x for which the series converges. You can see that our power series for number 91 is centered at c is equal to 0 because we don't have x minus any particular number. Number 91 will demonstrate that this series converges only at its center, only at x is equal to 0. Case 1 of theorem 9.20. However, to do the work for number 91, we must use the ratio test, or we can use the ratio test. It's the best way to go because you have a factorial expression here. So find the values of x for which the series converges. So how will we do that? We will use the ratio test to find the values of x for which this series converges. So with the ratio test, you must begin by finding this limit, and you want to find the values of x that would make this limit less than 1, because by the ratio test, those are the x values for which the power series will converge absolutely. If there are any x values for which the limit from the ratio test would be greater than 1 or infinity, at those x values, by the ratio test, the power series will diverge. If there are any x values that would make this limit from the ratio test equal to 1, you would have to do a different test because the ratio test would be inconclusive. So when you apply the ratio test for the power series in number 91, you begin with this limit. The limit as n approaches infinity of the absolute value of the quotient of the n plus 1th and the nth terms. So the nth term is just what's given in the power series, and we write that in the denominator. The n plus 1th term, you just replace n with n plus 1 wherever you see n. So now that we've done that, the next thing that we want to do is we want to simplify as much as we can. So n plus 1 factorial is 1 times 2 times 3 times 4 all the way to n, and then times n plus 1. So all the way to n is just n factorial times n plus 1 will give us n plus 1 factorial. When we write it like that, we're able to cancel the common factor of n factorial, that's in the numerator and the denominator. And using properties of exponents, x over 2 to the n plus 1 power can be written as x over 2 to the n times x over 2 to the first. You have a product of two powers with the same base, so when you add the exponents, you have the same thing. But when you write the x over 2 to the n plus 1 power as we have done here, you can cancel the common factor of x over 2 to the n, that's in the numerator and the denominator. So this is what we're left with, and when we look at the limit that we're left with, n is going to infinity, and we have the absolute value of n plus 1 times the quantity x over 2. And n starts at 0, but the more significant thing is n is going to infinity, so we know the quantity n plus 1 will be positive. So we don't really need absolute value for that. But remember, x is a variable. It could be any number, so we do need absolute value for that. But in this limit, it is n that is going to infinity, not x. X is considered a constant with respect to n, and therefore we may do the following. So this is an intermediate step where I just have the absolute value surrounding the x over 2, and I have n plus 1 just in parentheses. And then as we said, x is a constant with respect to n, so the absolute value of x over 2 is a constant that we can factor out. And here's the limit that we have. So as you can see, this limit, the limit of n plus 1 as n goes to infinity is infinity. So regardless of the value of x, the limit that we have in our problem will be infinity. The only value of x for which the limit will be 0 is when x is equal to 0. So for that reason, for example, if you choose x to be, say, 200, then you're going to have 200 divided by 2, which is 100. So if you have the constant 100 here, the limit will be just infinity. And in fact, regardless of what x is, if the absolute value of x over 2 is any constant, this limit that we just found will be infinity. The only exception to that is if x is equal to 0, because 0 times any number is 0. So we're going to state our conclusion for number 91. To give me some space, I'm going to erase this particular step that we had earlier. And the conclusion that we state for number 91 is the limit from the ratio test is equal to 0 when x is equal to 0. Therefore, this power series converges only at its center of 0. And that is what I just stated. The power series only converges at its center of x is equal to 0. So number 91 was a particular problem that demonstrates case 1 from theorem 9.20, where the series converges only at its center. Again, I'd like for you to take a look at the 9.6 lesson 3. There's an example there that demonstrates case 2, where there is a real number r greater than 0, and that is called the radius of convergence. And in that lesson, we also look at the convergence of the power series at the endpoints of the interval to determine what we call the interval of convergence. So you can take a look at 9.6 lesson 3 for case 2. We will now conclude our lesson by looking at an example problem for case 3, where we have a series that converges absolutely for all x. Number 92, find the values of x for which the series converges. And this is a power series. It is a power series centered at C. What is the value of C? You can write x plus 1 as x minus negative 1. It has to be x minus c. So the center of our power series is c is equal to negative 1. This example will demonstrate the third case from theorem 9.20, that the series will converge absolutely for all x. To determine the values of x for which this power series will converge, we'll use the ratio test. So we need to begin by forming this limit from the ratio test and find the values of x that would make that limit less than 1. Those are the values of x for which the power series will converge absolutely. If there are any values of x that would make that limit greater than 1 or infinity, those are the values of x for which the power series will diverge. And if there are x values that would make the limit equal to 1, we would have to do another test to test for convergence at those x values because the ratio test would be inconclusive. So we begin by forming the limit as n approaches infinity of the absolute value of the quotient of the n plus 1th and the nth terms. And we'd like to find the values of x that would make that limit less than 1, because then we can conclude by the ratio test that those are the x values for which the power series will converge absolutely. So the next step is for us to rewrite our limit as I've done. So we have the limit as n approaches infinity of the absolute value of the quotient of the n plus 1th term and the nth term. And of course you can write division as multiplication by the reciprocal of the divisor, and that's what I've done here. Furthermore, I've also rewritten the x plus 1 to the n plus 1 power as x plus 1 to the n times x plus 1 to the first. We have a product of two powers with the same base, so when you add the exponents, it is equivalent to x plus 1 to the n plus 1 power. And I have also rewritten the n plus 1 factorial as n factorial times n plus 1. So doing that allows me to cancel common factors. So we can see a common factor of n factorial in the numerator and the denominator that we can cancel. And we can see a common factor of x plus 1 to the n that we can cancel in the numerator and the denominator. So when we cancel all of the common factors, we're left with what we have here. And again, the important thing for us to understand is we're taking this limit as n approaches infinity, and x is a variable. It could represent some number, but once you choose x to be a particular number, no matter what that number may be, it would become fixed. And with respect to n, x is a constant. Furthermore, I only need to put the absolute value around the x plus 1. Because n is going to infinity, so 1 over n plus 1 will be positive. So with the discussion about x being independent of n and x plus 1, the absolute value of x plus 1 being a constant, you can factor out the constant out of the limit. Or you don't have to factor it out and you can just consider what the limit would be. As we just stated, this quantity that I'm now circling in green is just some constant value for a fixed value of x. Again, you can choose x to be any number, but once chosen, it is fixed. So you can choose x to be something outrageously large, like 20 trillion, but once you choose x to be 20 trillion, it is fixed at 20 trillion. So the quantity x plus, the absolute value of x plus 1 is just a constant. And we have a constant over n plus 1 as n goes to infinity. So that limit will be equal to 0 for any value of x. And because we've just found that the limit from the ratio test will be less than 1, will be 0, for any value of x, we may conclude by the ratio test that the power series converges absolutely for all values of x. So this problem that we just did demonstrates case 3 of theorem 9.2 about convergence of a power series. Here we have a series that converges absolutely for all x. I will now write the conclusion that I've stated verbally. I will just give myself some room by erasing this intermediate step from my work. So this power series converges for all x. The radius of convergence is infinity, and the interval of convergence is from negative infinity to positive infinity. So this is what we just saw in the problem that we looked at now. The series converges absolutely for all x. The radius of convergence is infinity. And in the example prior to that, we saw a series that converged only at its center, and the radius of convergence was 0. So today we looked at the definition of a power series. We were able to find the radius of convergence of a power series. For endpoint convergence, I am referring you to a prior lesson, 9.6 lesson 3, to demonstrate the second case from theorem 9.20 about the convergence of a power series.